Well, first of all, I'd like to thank you all for taking the time to listen to this this session. This is really an overview of this particular application and what we refer to at Woods as tunnel and metro ventilation. It's probably for people who are maybe reasonably experienced with the use of fans for industrial or HVAC applications. And I'm going to go through some of the specific requirements or considerations that we have to take into account because of this application, and then really how that can have a bit of an impact on the products that we select. Tunnels and metros is just really one of the applications where Woods supplies products, but these kind of projects that we call infrastructure projects tend to be a little bit more complex. They tend to have much more detailed specifications and requirements, and they can also be of a reasonable value, mainly due to the size and the quantity of equipment. Okay, so what I'm going to cover in the next hour, hopefully easily within the next hour, is for these kind of applications, so for metros, high-speed rail and road tunnels. Initially, why do we ventilate? And then for metros and rails, rail projects, what determines that ventilation rate? What parameters have to be taken into account? I'm going to talk specifically about a thing called a pressure pulse, which is a very specific implication of operating fans for metros and how that has an impact on stresses on the blades of the fan. Talk a bit about blade design, about how we've got around that particular issue, but how that new blade design has an impact on the power and efficiency of the system, and I suppose a summary of the mitigation. How do we deal with this particular requirement? And I've got some details of a sort of a fairly typical room layout, just to give you a feel for the size and the equipment and service that maybe we could provide. Then we'll do the same for road tunnels. And I'll be talking about what determines the ventilation rate, a little about the product range, and then really for these kind of projects, quite an important part of it is the QA or quality in terms of routine tests and what we call factory acceptance tests. So for metro and rail, what we're really talking about for metros is mass transit, urban rail systems. And then for rail, we're generally talking about high-speed rail, which is linking together two urban locations. And then for road tunnels, okay, there's a nice picture of some fans under test here. Yeah, so we're just talking about road tunnels in urban locations, mountainous locations, just to get through the other side of the mountain, or subsea under rivers. Why do we ventilate? There's two primary requirements, and it's what we would say is air comfort and smoke extraction. Okay, so depending on the particular project, those requirements are slightly different. So for most metro projects, it's about heat removal because there's a build-up of heat underground, and the fans need to be used in a fire situation to remove smoke. It's similar for rail projects, although depending if the trains are diesel, then there's an added requirement to remove pollution as well from those tunnels. And for road tunnels, generally it's pollution, so it's carbon monoxide, nitrous oxides, diesel particulates, and again the requirement to be able to operate the fans to assist evacuation of people in a fire situation. So looking at rail and metro projects, this is just a bit of an overview of some of the design issues that have to be taken into account. So for metros, it is relatively specialised design, and it can be quite complex, mainly because you've got a number of underground structures that are interconnected at a number of different locations. and potentially there are lots of different scenarios about what the trains are doing. So where the trains are, whether they're stationary or moving, whether there's one or two trains, the direction of movement. So it can build up quite a bit of complexity in terms of the number of different scenarios that have to be considered. And one of the big issues is the movement of the trains themselves. So they can assist the sort of self-ventilation of these underground spaces, but there's just generally a problem with the movement of trains, the fact that they then move additional air around this space, and that can have an impact on the fans, and it can put the fans under, if you like, slightly abnormal operating conditions. So we need to understand that and make sure that we've taken that into account. All the heat from the electric motors, from people, that's all effectively discharged into this space. So we need to be able to make sure that we deal with that heat and we don't get excessive heating underground, because it wouldn't be very pleasant to be in that space. You've got the heat from the brakes. If the trains are air conditioned, all that heat is rejected generally into the tunnel. And you've also got potentially air conditioning in the stations, which again, that heat is then discharged into this underground system. Those tunnels can be used for both supply and extract, and we'll come on to this later, but generally the fans have to have the ability to work equally in both directions to give, if you like, maximum flexibility in how the system can be operated. So you've got these long tunnels, you've got trains in those tunnels. We can use large fans, or we can use a thing called a jet fan, and we'll talk a bit about that later. As I said, those fans generally have to be reversible. In our case, we offer 100% reversible fans, but it can also be quite complicated by the fact that you've got a length of the train, and particularly in a fire situation is, that fire could occur literally at any location along that train. So how does the ventilation system accommodate that? And I think the main thing here is, in an emergency situation, it's about trying to keep the escape routes clear of smoke. It's smoke that kills people, not fire. So it's critical that the smoke is kept away from people to allow safe escape from these underground spaces. And the fans themselves are rated for a range of different temperatures. So this depends both on local legislation. So most countries have a particular requirement for the fire rating of the fans, and also if it was done correctly, someone would do some quite detailed design based on design fire, and would say, the fans need to be rated for this. But typically fans are rated for 250 degrees C for 2 hours, 300 degrees C and up to 400 degrees C, all for 4 hours. Okay, so still talking on the subject of metros, there's a variation in the operating pressure for the fans, and it's only to do with the movement of the trains. So effectively, we've got a tunnel, and we've got a train moving through that tunnel. So it acts like a piston. So in front of that fan, there is a large plug of air, which is basically pushed through the tunnel, can then escape into the station area. But also, depending on how the system is designed, it will want to go through the fans. So it can put a pressure pulse on the fan. Now, the drawing in the background there, which is, the picture in the background, showing a sort of very open station, whereas in reality now, pretty much all modern metro systems incorporate a thing that's called platform screen doors. So these doors effectively separate the train from the station. Okay, and there's two main reasons for this. Is one, it's to help isolate the space and improve comfort. So it means you can actually air condition the station areas and the train areas, and also it's to stop anything getting onto the track, including people. So it separates people from the operational part of the train itself. So it much improved safety underground. Now, depending on where you are, in the world and the design of the system, this pressure pulse can be anywhere from 300, which it typically used to be, up to say 700 for the MRT system in Singapore. And I have seen projects elsewhere in the world where it's been double that, so over 1400 pascals, so very, very high. And this happens every time that there's a movement of a train through a station. So effectively, when the train comes in, you get a build-up of pressure, so you get a positive pressure. The train then stops, the passengers exit the train, and the train then moves out, and then potentially you then get a negative pressure as the train pulls away on that side. So if a fan is connected from the tunnel to outside to atmosphere, that fan will see that pressure pulse or that change in pressure on every train movement. So that can be, you know, hundreds of times a day that can happen. So you might think, okay, well, who cares? What's the implication of that? Now, to understand what that means, yeah, we need to have a bit of an understanding about the performance curve of a fan and how axial flow fans operate. So what I'm showing here on the left-hand side is a fairly typical characteristic for an axial flow fan. So we've got volume across the bottom, pressure up the side. This solid black line here represents the system curve. So this is the relationship between the required volume and system resistance of the system, and it shows how it varies from 0 up to the design operating point. This black line here represents the fan performance curve, okay, and where those two lines intersect is effectively the operating point. So it's where the fan performance lines up with the system performance, and that becomes your operating point. But what can happen is if there's a positive or negative pressure from the movement of the trains, this will effectively start to push this operating point higher and higher and higher. And then it goes to a point of what we call, it's getting close to, or it can go into an aerodynamic stall, okay, which effectively is an area of sort of high turbulence, low efficiency, increased noise, but more importantly, it increases the fluctuating stresses on the blade, which if it was to continue for a period of time, could potentially lead to failure of the impeller, you know, the blade and the hub components, due to this excessive stress. The drawing on the right is really trying to explain what's actually happening in this stall. So what we're showing here is a sort of typical aerodynamic shape. So the best way of thinking this is as an aircraft wing. Okay, so an aircraft wing, it's slightly bigger on the top. And so as the air goes over, it has further to go across the top. You get a reduced pressure, and that reduced pressure causes lift. Okay, aerodynamic performance. And what you want is you want the air as it goes over the top of the aerofoil to stick. And in this example, it does. But if that angle becomes excessive, the air can start to separate. So the air here is no longer sticking to this aerofoil section, it's carrying straight on, and then it creates this area of turbulence or vortices as the air effectively doesn't stick to the aerofoil shape anymore, and that can cause very high stresses on the blade. So to show that a little bit more clearly, we've got this graph. So it's drawn slightly differently, but it's the same information. So the solid black line represents the system curve. The solid red line represents the fan performance curve, and where the two intersect, that's our normal operating point. Okay. Now these curves continue and they show this sort of dip in performance. So this is what we would determine as the stall area. But what's important to look at here is this dotted red line, and this represents the fluctuating stresses that feature on the blade, on the fan. So as you can see, under normal operation up to the stall, steady state, sorry, the fluctuating stresses are relatively low and they're well within the safe mechanical properties of the material. But as you approach the stool, the stresses get very, very high to a peak, which is around this point here, and then they start to reduce again. So potentially, if the fan was to be pushed into an outer stool, it could go through this area. It's a very high fluctuating stress. As I said earlier, one of the requirements for these kind of projects is that there's nearly always a requirement to have both supply and extract. So if we were to use this traditional aerofoil section, could we use it in the opposite mode? You know, could we use it for extract? So this graph, we've still got the same information in red, but what we've done now is we've overlaid that with the fan running in reverse. So you will get some performance from an aerofoil, a unidirectional aerofoil, if you run it in reverse. But what's really important here is to look at the potential stress levels. It goes into a stool very early because it's not really designed to run backwards. So it's the same principle of trying to fly a plane backwards. It doesn't do that. It only flies forwards, and it won't like flying in reverse. But what we could end up here is if we were to use this fan to give some kind of flow in reverse, those fluctuating stresses would be high. They would exceed the safe limits of the material, and over a period of time, which could be days, weeks, months, maybe years, would actually work hard on the material and could lead to a mechanical failure or a breakup of the blade. So probably 40 years ago or 30 years ago, we looked at this and we decided that, okay, what we need to do is develop a solution where we can get the same performance in either direction. So we developed what we determine as this sort of fully reversible section. Okay, so the top image here is the traditional aerofoil section for a unidirectional fan. So it's sort of round at the front and it tails off at the back. This is similar to an aircraft wing because it's all based on the same technology. And then this reversible section is that basically you have this top profile, which is a sort of modified aerofoil section, is then mirrored underneath. Okay, so this kind of design of blade gives you 100% reversible performance. So you get the same flow, pressure, and efficiency in either direction. Okay, which is good. It's good for this application. The only thing is that there's always a bit of a trade-off, and because it is this truly symmetrical section, it's not as efficient as the unidirectional design. So there's a trade-off that you get performance in either direction, but you don't get quite the same efficiency. So which has to be taken into account into the design. And just looking at the same kind of graph showing the fan performance. So in red, solid red, this is the fan performance curve, and then this dotted line represents the blade stress. So in this example here, we're showing the forwards and reverse together, but as you can see, there's no difference in the fluctuating stress levels, whether it's running in forwards or reverse, and it's well within the safe limits of the material. So this impeller can be operated in either direction indefinitely, and in fact our design approach to selecting the materials and the stress levels on the blades and the hubs is effectively that the steady state and the fluctuating stresses are designed for near infinite life, and there's a safety factor in there as well. So if they're operated normally within the normal limits, you have an indefinite life from those impeller products. So that was how we, if you like, that's how we got around this issue of having a fan that can operate in both directions. And I think what's important to understand is that there is always a little bit of a trade-off. So in this example here, this is just a a fairly typical fan, and I'm just really showing the difference between a unidirectional and reversible fan. So in this example, the unidirectional fan has a total efficiency of 79%, so it's using 100% of the power. To get a reversible fan to give the same performance, we're up on power about 10%, and we're 5-6% down on efficiency. But you do get that performance in both directions. So there's a little bit of a trade-off. And also, when you go to high temperature requirements, generally you then have to have an increased tip gap around between the blade and the casing, because the blades are made of normally made of aluminium, or even if they're made of steel, they do increase in size as they're heated, and so you have to make sure that there is sufficient tip gap. So again, the higher the temperature, bigger the tip gap. The bigger the tip gap, it leads to a slight loss in efficiency. So we're always trying to, if you like, manage the compromise between getting the best performance, but also a product that can be used in life safety. So we talked about this pressure pulse earlier, and what it could do to the fan. We typically have 3 different kind of solutions to this problem, and I'm just going to run through them. And if I'm honest, there's not one solution that suits every project. It's one of the things about this kind of application. It's you need to try and understand what's being done, how the system operates, and how best to respond to that with a product that meets those requirements. You know, in my opinion, one product isn't the best solution for every project. So our first option here is that we can select a fan that has a relatively low angle at the tip of the blade. That's where we measure our angles, so right at the tip of the blade. And if that angle is low, we have what we call a non-stalling pitch angle. So in this example here, you can see that most of the curves, the different pitch angles. So we're starting here on the left-hand side at a low pitch angle, increasing up to the maximum for this fan. But at these higher pitch angles, the curves are effectively cut off. So you're not allowed to operate the fan beyond that point. But at these lower angles, the curves basically continue and almost go up to zero flow. So these are what we call a non-stalling pitch angle. You can operate the fan safely anywhere within that region. It won't cause any mechanical damage to the fan, but the trade-off is that it will give you potentially lower efficiency. So for axial fans, where I'm showing the red dot now, generally represents peak efficiency. So around 2/3 up the curve and 2/3 into the pitch angle range generally is peak efficiency, and it's a bit like a bullseye or a circle that comes out from that, and the efficiency gets lower and lower as you move out. But again, it's more important that the fans operate and are safe to operate, and there's a slight trade-off in terms of lower efficiency. The second choice here is to select the fan on a very stable part of its characteristic, so it can cope with this positive and negative pressure pulse. So the example here, this black line here represents the system curve. So this is our initial operating point. We're showing in this example a +500 and -500 pressure pulse. But both of those operating points are still on the steady part of the characteristic. So this fan would operate quite comfortably forever or indefinitely in this mode, and you've got a design operating point. So as the trains move through the tunnels, the duty point moves up, comes back down to the design duty point, and then goes down, and it can do that quite happily forever. But it's not always possible to get a selection where you can meet that, particularly if the pressure pulse gets higher and higher. The third option that we have, and this example here, we've got a design operating point here, but we actually need 1,000 pascals pressure pulse, which would take you over the top past the stool, we can fit what we call an anti-stool device, which effectively is a sort of specially modified duct which sits around the impeller. And what it does is it helps to deal with what's happening during the stool. So what happens at this point around the stool is that the air can start to reverse direction because it's an unstable part of the characteristic. The airflow goes back in the wrong direction and causes these high stresses on the blade. But we have this small section of duct here, and this allows the air to go back and to rejoin back into the airflow and go back through the impeller. And what it does is it has the effect of reducing those stresses. And what you end up with is this dotted red line here, which represent the normal fan curve, showing this sort of stool. But the performance curve sort of carries on and keeps going up. And this stool situation here is greatly reduced. And again, the stresses on the blades are reduced, and therefore it becomes a safe operating condition for the fan. Yeah, there's no, it won't cause any damage to the fan. Again, as I said earlier, there's always a bit of a trade-off, and as far as we're concerned, you can have an anti-stool chamber or anti-stool duct, but it does have an impact again on the efficiency, and they're okay if the stool is in one direction. If the stool could occur potentially in both directions, we don't see it as being particularly effective with that. So it's important again to understand how the system operates. Now, the important thing potentially with this is that this stool generally only happens, or can only happen, when trains are operating, and potentially in many fire situations the trains are actually stopped. So the trains don't run in and out of a tunnel when it's on fire. They either move into the station or stop, or they're held in the tunnel. So this pressure pulse doesn't always occur during the fire situation. But again, it's important to understand how the system is operated, so you can understand how it has an impact on the equipment that's being supplied. So in summary, when it comes to the pressure pulse, there's three basic methods of dealing with it. So you can have a low non-stalling pitch angle. You can select it on a steady part of the fan characteristic, so there's no implication of it going into stall. Or the third one, when you can't use the above two, is to fit an anti-stall duct. And so yeah, we've offered fans in all these three different configurations. If I'm honest, number two is probably our preferred option, mainly because we see it as the best compromise in terms of meeting fan efficiency and ease of use in terms of the system. Okay, so I'm now going to look at a typical installation. Okay, so this is a real project where we supplied the equipment for a tunnel. So we've got our fan in the middle, the round thing, and these large square boxes here are silencers or attenuators. So there's one going to atmosphere, to the outside world, and there's one going into the tunnel. Generally, there will be a damper connected to each fan, so it can be isolated from the system. And it's very common to have two fans in parallel, a run standby situation, and then we have to have a transition from the fan to the silencer to connect it together. The use of cylindrical silencers wouldn't really be sufficient for this. The fans produce a reasonable amount of noise, and the design criteria for noise is generally a lot lower, so you have to go to a rectangular silencer to meet the noise level. And just to give you an idea of the scale, just to prove that this is a real project, so this was the fans, or one of the fans that was built for this project. This is towards the larger end of our range, so this is actually a 2.8 meter diameter fan. It's built in multiple sections to allow it to be disassembled in situ. and I think it had a 5 to maybe a 600 kilowatt motor. So it's a very substantial industrial fan that was supplied to this project, and it's 100% reversible, so the fan can be operated equally in either direction. Okay. So in terms of those additional elements, obviously, Wood is a fan manufacturer, so we'll obviously supply the fans, but we'll also we can design and supply the transition ducts, and where possible, we always try to influence the design of those to optimize them. So on this particular project, we have effectively a two-stage or a two-section transition. So there's a round to square in the first section, and then we've got a square to square in the second section, and they're at slightly different angles. So what we did there was designed it in that way to try to reduce the pressure drop as much as possible. And again, these systems generally need to be symmetrical because we want to be able to operate in both supply and extract mode. So we want to have a similar system resistance in either direction. Okay, they're generally made from mild steel and similar to maybe to the fan casing. They can be hot dip galvanized. It provides an extremely durable finish, which is generally acceptable for the application. These fans are normally mounted inside the building. They're not subject to the atmosphere, so it's a reasonably okay environment. And you easily get your 20, 30-year life from the casings. And those transition sections are normally made in pieces to allow easier transportation, and more importantly for movement and installation on site. So to move them in one piece would be quite difficult. So the second element there is that we had on that layout was the silencers. So again, you're going to need a silencer on the system side, so the noise going into the tunnel, into the platform, and going outside, out to street level. So if this is a metro, it means it's in an urban area, which means the discharge is close to where people are living. So it's important to have a reasonable amount of attenuation to reduce the noise. Those silencers or attenuators need to be designed to meet the same criteria as the fans. So if the fans are rated for 400 degrees C for 2 hours, then the silencers need to be as well. Again, it's a mixture of different ways that they can be supplied. It's quite common, as shown here. I don't know if you can see that, but these splitters here are effectively built into the structural element of the building underground. So the concrete walls and floors become the casing of the silencer, and these splitter elements are stood in vertically and fitted into that concrete structure. They're generally pre-galvanized or manufactured from pre-galvanized steel, could be painted, and sometimes will have stainless steel perforated sheet. So these splitter elements have acoustic grade mineral wool or rock wool inside, but it needs to be held in place. So generally we would use perforated sheet steel to make them very durable, but also it means that the airways are kept the correct size, so there's no impact on performance, particularly in the fire mode. You don't want the silencers to start to close up. And the last element here would be these the fire rated dampers. So again, the fans are normally mounted in pairs, so there's a sort of a run and a standby one. If one of the fans was to go down, you wouldn't want the air to be recirculating around the fan, so you need the ability to isolate it, so the system still works, and also gives the ability to work or maintain the equipment because it's isolated from the system. Again, they need to be rated or certified for the same temperature as the fans, so you have a complete system which is all certified for the application. You want them to be relatively low loss as well, which generally they are, and also there could be requirements that they of quite low leakage. So if the fan is shut off and the damper is shut, that the air is still not leaking through that part of the system. Okay, so that's a, if you like, that's a bit of a quick overview of metro ventilation. I can see there's a few questions. I think if it's okay, I'll carry on with the just to finish off, talk about road tunnels, and then I'd rather have more time at the end to deal with any questions that come up. So the second main application is road tunnels. This is probably where we started our business in terms of tunnel ventilation, and for this particular requirement or this particular application, when it's road tunnels, we're talking about dealing with pollution and what to do in case of a fire or emergency. Okay, these systems and the way they operate and the way they're designed has certainly changed in the last 40, 50 years. So I'm just going to quickly run through the different types of ventilation, but what's shown here is a system using jet fans. This has certainly become the most popular method of ventilating road tunnels, but there are some limitations or some issues associated with it which you have to be mindful of. So the original form or method of ventilation for tunnels was what's called a fully transverse system. So what we've got here, hopefully you can see that, is that basically at the top of the tunnel we have a duct, and then low down or underneath we have another duct, and effectively they operate as supply and extract. So in this sort of schematic here, we've got supply coming from the floor, and then extract is being taken out at high level. So this generally requires the use of very large fans, because you're talking about moving large volumes of air, and the fans are made outside of the tunnel. It's probably the most exact kind of ventilation, because effectively it's like cross ventilation. You know, fresh air comes from here and is extracted out very closely to where the pollution is. So it's very good for pollution. You can have an almost unlimited length of tunnel. It's probably the only real safe way if you have what's called bi-directional tunnels, where you've got traffic in either direction. Again, that's pretty much been designed out because it's inherently not particularly safe to have traffic moving in opposite directions in the same tunnel. So it's probably one of the first ways it was done, but it's probably the most expensive way of ventilating a tunnel, not because of the fans, but just because of the civil costs. So, you know, this tunnel is a lot bigger because you have this very large duct underneath the road and above. So, you know, there's quite a high construction cost. And normally in the ceiling here within this this large structural duct would be a whole series of dampers. So for normal pollution ventilation, all the dampers would be open and it would be ventilated. But in the case of a fire, you would then only open the dampers close to where the fire has been detected. So the smoke is extracted as locally as possible to where the fire is, to stop it spreading throughout the tunnel. That's type of system. The fully transverse system then progressed to what's called a semi-transverse system. So it's very similar, but now there's no duct, if you like, in the top. We've only got a central extract point, so it's really relying on what we call longitudinal ventilation. So, you know, all the air is being moved along the tunnel to the extract point, but you still have this supply duct. So it is better in terms of pollution control, and it is maybe a common method that's used for very long or congested tunnels because it helps to dilute the pollutants. Okay, so it's a little bit cheaper than a fully transverse system, but probably the most popular at the moment would be what we call a longitudinal system, using a nice shiny red jet fan like this. So in this situation, we actually use the tunnel itself as the duct. So there is no additional duct work. We mount the fans inside the tunnel, and we basically bring in fresh air from one end. We push the air along and then we either push it out the other end, or if it's a particularly long tunnel, we have to extract it and then reintroduce fresh air. So the issue potentially with this, particularly in terms of pollution, is that you've only got one access point for the fresh air. So the air becomes increasingly polluted, and there's nothing you can do about that. And if it exceeds the required levels by design, you then might need to have a mid tunnel portal to extract the air and then reintroduce fresh air and then continue using jet fans. So these fans are mounted inside the tunnel, and obviously they're fully immersed in the tunnel itself. This system is particularly good when it's a unidirectional tunnel, so when the traffic's moving in one direction, and it has a very simple premise when it comes to a fire. So in this example here, if this vehicle was on fire and had stopped, the jet fans would come on and they would blow in the same direction as the traffic movement. And what it means is that anyone who's in front of the vehicle that's on fire, is in their car, is able to drive out. So they can just drive out. There's no obstructions to them. They just drive out of the tunnel. So this side of the tunnel becomes clear. Anyone who is stuck in front of the fire, the fans are pushing the smoke in this direction. Okay, and as long as you achieve what's called the critical velocity, which is a minimum velocity by design, normally around 3 meters per second, that will stop the smoke back layering and coming back, and it keeps this area of tunnel completely free of smoke. So it just becomes a safe area to be. As long as the fans are operating, the smoke is only being blown in the same direction as the traffic was moving. So it's a very simple premise, and it works very well. The very last version of this, which we've seen a few of these, it's what's called a Staccato nozzle. It's using exactly the same principle as longitudinal ventilation with jet fans, but in this case, there is no room in the tunnel, or potentially no room in the tunnel for even jet fans. And so what actually happens is the fans are mounted outside, okay, and they blow the air in, but they blow in through a nozzle. So they create a very high velocity, just like a jet fan, and they push the air in at high level. So this sketch on the right hand side shows us effectively a complete system. So we've got a fan with a transition and a silencer, and then there's special piece of ductwork, and the air is injected in at very high speed. So it behaves in the same way as a jet fan. The only thing with these kind of systems is they only really work in one direction, because that nozzle only blows in one direction. So it's difficult to have a system that could be reversible when you're using Staccato nozzles. So in terms of what you have to consider when you're designing the ventilation system, so normally for these kind of systems, you end up with at least 4 different types of calculations to work out what is the design parameter. So you need to work out what the different pollution rates are, which is based on the number of vehicles, the size of vehicles, the age of the vehicles, and what emissions they have. And you would then normally look at the carbon monoxide output from the vehicles, and then work out how much fresh air you need to dilute that down to the design criteria for CO. You need to look at nitrous oxides, particularly from diesel vehicles, which is a bit more in vogue at the moment. So you need to look at that to work out the fresh air requirement. You've got issues of visibility as well. So there are particulates from diesel exhaust fumes, which can affect the visibility. So there'll be criteria for visibility, so it needs to be diluted as well. And then there would be the final one, which would be the fire design, which will be a case about working out what is the critical velocity. So you end up with these 4 different requirements. That's an amount of air or volume flow through the tunnel. And then you then convert that into a thrust, and I'll go into that in a little bit in a moment. So some of the other considerations are if you have 2 tunnels side by side, and you're using jet fans, if you like, fresh air is coming in one end and dirty air is going out the other, or polluted air comes out the other. Potentially some of that air could then be drawn back in to the tunnel next to it. So there is an element of some recirculation of that pollution, and also that pollution is at low level. So if it's in a residential or an urban area, the pollution is coming out of the tunnel, and it's not necessarily being pushed up out of the space. So there's a special resistance, a special system resistance calculation. The basic principle is that you work out the required volume flow of air for those different scenarios, and then you have to work out what is the resistance of taking that volume of air through the tunnel. So there's an inlet loss, there's a frictional loss along the tunnel, and there's an outlet loss. There's the effect of the vehicles. So in this drawing here, I've only got cars, but you can imagine if you've got lorries, they start to block up the tunnel a little bit. So there's a bit of extra resistance, and that then gives you a required pressure drop. If you convert that pressure drop, multiply it by the area, you get a thrust in newtons, and that's how jet fans are rated. So that's how they're tested. So let's take an example. Say we work out we need 10,000 newtons to overcome all the losses to get the air through this tunnel. If each fan produces 1,000 newtons, I need 10 jet fans spaced in the tunnel to give me that required performance. Okay, they're normally installed in 2s or 3s or 4s, depending on the size of the tunnel, and also they have to be spaced out throughout the tunnel, because what you don't want is you don't want them too close to each other longitudinally, because what can happen is that the discharge jet is then being effectively sucked in to the next fan further down, and it starts to offload the next jet fan. So you need a considerable distance between those fans. Typically it's 70 to 100 meters minimum distance between jet fans. Again, these fans can be rated up to 400 degrees C, depending on where you are in the world, and they'll be certified. And another important thing is, we need to maintain a noise level in that tunnel. Not when you're in your car and you're driving, but in case there was an emergency and you had to exit your vehicle, you would want to be able to hear any messages or instructions being issued from the fire brigade. So the good thing about having, I suppose the reasonable number of fans is it gives you a sort of stepped performance in terms of ventilation. So you can have 2 fans running, 4, 6, 8, 10, or whatever it may be. So you can have this system that responds to the measured pollution and then can ramp up. In some countries, particularly in Japan, they tend to have all the fans operating but use them on variable speed drives. So they'll have all the fans running at a lower speed, but it's doing a similar job. But it's just their approach to how they do that. One of the big issues that can affect the operation of these kind of systems is the effect of the wind. So if the opening to the tunnel is particularly exposed or wind is in a particular direction, it can have a significant impact on operation of the system. So quite often jet fans are reversible, and if the wind is particularly strong, you may change the direction of ventilation, so it's blowing in the same direction as the prevailing wind. So we're using the benefit of, if you like, free or natural ventilation, but that has less of an impact on longer tunnels. So I've only got a couple of bits left. So just to think about the product range. Okay, so large axials, we consider them from 1600 millimeters up to 3.1 meters. You can have them suitable for one direction or both directions, bidirectional reversible, and they can be certified for 200, 300 or 400 degrees C for 2 hours, and we have extensive ranges of those. The jet fans are a much smaller range, so they're generally 500 millimeter up to 1600 millimeter. Again, unidirectional or true reversible. I would say that probably 90% of the products are reversible. It's a very common requirement, even if they're not really needed to be reversible. They're nearly always specified as reversible, and they are tested and certified for 200, 300 and 400 degrees C. So the only last thing I wanted to just quickly touch on was, on these kind of projects, it's quite common that there's a requirement to have what we call a factory acceptance test. Okay, and it's mainly because it's a particular design requirement. You know, it's generally quite a high performance specification, and the larger fans sometimes are, I wouldn't say bespoke, but they are very much project specific. So it's quite important that the actual performance of those products is tested and guaranteed. So we have a dedicated facility to test the fans. This is just showing the standard test rig. So as you can see, to do an aerodynamic performance, you end up with a lot of ductwork, and particularly when you have a 2.5 meter fan, it becomes an extremely long piece of ductwork. But I think the important thing here is that, you know, the fan should be tested. It should be tested in a certified laboratory to a recognised standard, either to an ISO international standard, a European standard, a British standard, or the a US AMCA standard. We generally test our fans to the large axials to ISO 5801, which is a test arrangement for ducted fans, because that's generally how they're installed. And there's also an equivalent acoustic testing procedure, which is the semi-reverberant procedure, ISO 5136. And then the jet fans are generally tested to ISO 13350. And so what that looks like, this is a typical arrangement for a jet fan. So here's our fan. This has got silencers on the inlet and outlet, and it's on a thrust rig. So the fan is operated, and there's a load cell, and you get a direct reading of the axial thrust. So if it's designed for 1,000 newtons, you know, you basically can read off exactly what that fan is producing in terms of thrust. And yeah, this is just the second part. This is how the noise is measured. So it measures the complete unit in a semi-reverberant environment, which is similar to the environment of when it's installed in the tunnel. So in summary, we talked about metros, rail and road tunnels, why we ventilate, what are some of the considerations for ventilation for metro and rail projects. Talked quite a lot about the pressure pulse and how that can impact the stress, the fluctuating stresses on the blade, and the requirement to have airflow equally in both directions, and how that impacts the blade design, and the knock-on effect on power and efficiency, and what are some of the mitigation methods you can use to deal with the pressure pulse. We looked at a pretty standard layout of a plant room, then talked about tunnel ventilation. Again, what things determine that in terms of the ventilation rates. So it's pollution for carbon monoxide, nitrous oxides, and diesel particulates. And then we have a design for smoke removal, a bit about the product range, and then just a little bit about testing, and particularly factory acceptance tests. And that was what I was going to say.